We've been studying these line integrals involving vector fields, where we have a curve here, maybe starting off with point A, and it goes up here to point B. We have a path, and maybe this curve was modeled by some, vector valued function. We have x of t, y of t. And you may have wondered, well, can't we just use the fundamental theorem of calculus? Can't we just find the antiderivative of that vector field, plug in the b, and then subtract off plugging in the a? And the fact is you can. Yeah, you can do this. You can write this as f of b, where b is a point. It's got an x and a y, minus f of a. You can do that, provided that this thing exists, provided that you do have such a function. In other words, provided that there is some potential function out there that is actually this vector field. The gradient is the vector field. In other words, if your vector field, the big F, is a gradient field, or another way to say that, if it's conservative, then you can do that. Yeah, you can find the potential function and just plug in those values. Because look, we're saying that this is true. Then that means I can rewrite this integral up here. And let's suppose down here, coinciding with point A is t equals 0, and this or t equals a, and up here is t equals b, let's say. So let's, just for my notation here, let's say that's true. So in other words, we could write this integral this way. The gradient f, instead of big F, I'll just do that, dot it with this thing. Yeah, I could do that. You just change my notation a little bit. Yeah, same thing. Now, remember the gradient of f. So let's think about this now. What I'm doing is I'm replacing the x and the y to be in terms of t. So I'm going to view f only along this curve. So let's look at this. Let's think about this thing. Let's do the partial of f with respect to t. Okay, now think about what that would look like. That would be using the chain rule, partial with respect to x, dx dt, plus partial with respect to y, dy dt. I mean, this is the chain rule right here. Okay, with that in mind, with this in mind right here, let's rewrite this thing. So here we go. We're going to go from A to B, and I'm going to have this. I'm going to put in this gradient. It's going to be partial with respect to x, dx dt, plus partial with respect to y, dy dt. Okay, and then, what I've done is I've rewritten this whole thing. Okay, and then dt. Okay, so I've put in the t's, and now I've got this function. Now, take a minute and look at this. This is just involved, the only variable we have here is t. The x and the y have been totally replaced by something involved with just t in it. So really, we could rewrite this way. We could rewrite this as d dt of what? Just f of xt, yt, and then dt. See? I could just rewrite the whole thing that way, and going from A to B. Now look, we've got the integral of a derivative here. Well, obviously, those kind of undo each other, and what we get is f of, well, x of b, y of b, minus f of x of a, y of a. And now notice f is the potential function. So it's like, we've used the fundamental theorem of calculus. And the terminal point, we started here at A and B and went to B. Well, x of B is the x coordinate of the point B, y of B is the y coordinate of point B, and x of A, x coordinate of A, and y of A, the y coordinate of A. So really, all we did was get the antiderivative and plug in. Now, one of the things that we can take from that is that the path is not important. It doesn't matter how we get from A to B. So we don't, we could have a complicated path or a simple path. It doesn't matter. We just plug in the top point minus the bottom point. We don't even care about the path. Now, here's what we do care about. Let's suppose you have a situation where you are starting at one point, going around, and you come back to the same point, so that you have a closed curve here. When you have a situation like that, you start and stop at the same point. So here's your starting point. Here's your stopping point. If they're the same, then this integral would equal 0. So here's the deal. If you have a conservative vector field, if f is conservative, and you have a closed path, then that integral is going to be 0. So these type of integrals right here, they're if f is a vector field that is a gradient field, so if it's a gradient field, this line integral is independent of path. This vector field is conservative, of course, and if it's a closed region, a closed curve like this one, then that integral would be 0.